Okay, this is lecture number 18, the final lecture where we finish up 10.5 about proportions, two types of proportions, such as the percentage of men that feel a certain way about a certain item, and maybe the percentage of females that feel a certain way about a certain item. And perhaps there's a difference in those proportions, and perhaps there really isn't much of one. And this is what 10.5 seeks to choose between, and gender acknowledgement is part of what is done, but there are many other proportions that are available to compare two different populations. We'll also, of course, have our final review, and I'm sure you're interested in that because this being dated for June the 4th, you have around a week or less to get ready for the final. Okay, so here we are in chapter 10.5. Two proportions, hypothesis testing, confidence intervals as well. 10 and 9 are very similar, except 10 kind of combines the confidence intervals from chapter 8 into the hypothesis testing of chapter 9. Okay, so let's get to the beginning of this. Inferences about the difference between two population proportions for what they will say are large independent samples. So that's great. So we'll be looking for the mean, standard deviation, and sampling distribution of the difference in the proportions. We'll look for confidence interval estimation of the difference in the proportions, and especially hypothesis testing about the difference in the two proportions. Is that difference close to zero, or is it far from zero? Okay, so the sampling distribution has the mean as being just exactly what you might would think it would be. There are no hats on those p's. Those are the actual differences in the actual proportions if you're able to get a population, which is sometimes not very likely. But anyway, there you have the mean, which is no surprise. Standard deviation is just algebraic derivation. This is in terms of the sigma for the difference in the proportions, and of course there's the examples. We really kind of use the S version of this mostly. And so if we're looking for just a confidence interval, then what we'll do is we'll start with the proportion, the sample proportion for the first proportion, and then the sample proportion for the second one. Take the difference, because all you have are samples, and you find what that difference is. Maybe it's positive, maybe it's close to zero, maybe it's negative. Z gets to be used here, which is also nice, assuming all the minimums are upheld, such as all those things have to be greater than 5. We'll talk about that again. And then we have this S, the sample standard deviation, with regards to the difference in the proportions, and so that's found down here. So there's a little bit of plugging in. Of course, if you want to show your steps on your TI calculator, that is acceptable, but you do have to show steps. I always get students that feel that they're above it all and don't have to show any work. I just don't understand that. I can't relate to that. Certainly points don't really come your way that well. So researcher wants to estimate the differences between the percentages of users of two toothpastes who will never switch. It's sort of a loyalty type of a deal. In a sample of 500 users of toothpaste A, 100 said they would never switch. In another sample of 400 users of toothpaste B, 68 said they would never switch. So if P1 is the proportion of the users of toothpaste A, P2 is the proportion of all users of toothpaste B who would never switch, what's the difference of the two? The point estimate is simply to find out what those numbers are and subtract them. Very easy. Point estimates, I don't feel they're even worth putting on the final exam, but you do see them on occasion. And yeah, this book loves the 97% confidence interval. I do not plan to give you that. I plan to give you 90, 95, and 99, and alphas of 0.01, 0.05, 0.10. Okay, so we find the basic proportions. Yes, 100 out of 500 is just what you thought, 20%. And then the toothpaste B only has a 17% loyalty. And yes, you have the Q's that go along with them. They're not that important right at the moment, but they will show up. So you have 80% from toothpaste A that are not loyal, and 83% from toothpaste B who are not loyal. Okay, so the difference between toothpaste A and toothpaste B shows a net plus for toothpaste A, loyalty-wise, of 3%. Not zero, it's a positive number, 3.03. And then they do the double check for legal purposes, make sure they're all greater than 5. Yep, they are all greater than 5, so we're good to go. It's always a good idea to check that if you have time. I do recognize that as an accomplishment. If you do everything else perfectly, sometimes I don't really notice, but if you do happen to make a misstep here and there and you happen to show this, it's sort of a replacement for some of that, credit-wise that is. So it's certainly not any harm done. If it doesn't take you that long to do, by all means, show it. But they're all greater than 5. Both sample sizes are large. That is, greater than 30, of course. And we use the normal distribution to make a confidence interval for P1 minus P2. And actually, we don't have to worry about the 30 here. All we really have to do is look at the greater than 5 in section 10.5. So I misspoke there for just a second. And we'll use the normal distribution. And the first thing to do is to find the standard deviation of that difference in the proportions. And they did not show all the numbers being plugged in. But when you do that, you will get an overall sample standard deviation of about 0.0259. And that will be instrumental because that's used down here in the formula. We'll have to find the difference of the proportions, which we already found to be 3%. And then we'll type in that 97%er for the Z, usually little used, 2.17. It's not on the standard list. You won't have to worry about it. But you do multiply Z times S, and Z times S will give you a margin of error of about 5.5%, 5.6% if you want to talk percentages, and you simply add and subtract it and put it in proportion form. We don't have to have percentages. I do notice that both of these are above 0, which does seem to show a definite difference. And actually, there's a mistake here. I take that back. They're not above 0 because this is a negative. They lose some of the typing printing ability when I transfer the slides for some unknown reason. So yeah, when you subtract 0.056 from the 0.03, yes, that's a negative. So we might have a difference that when you take the A minus B difference, you see a negative number. That simply means that B happens to have more loyalty than A in this particular case. But it's leaning stronger towards the A greater than B because it did have a 3% head start after all. So, but yeah, it could go either way because the margin of error is rather large. 5.5%, 5.6% margin of error. Okay, so here's the test statistic Z for the difference in the proportions as far as the samples are concerned. And all we're interested in is that P1 hat minus P2 hat. We always subtract that second half of the numerator. We're just not interested in that. That would be where handicaps could go. We're not using handicaps here. So we will take the value of P1 minus P2 substituted from HO, which is always 0. So that's just a side comment saying, don't worry about that second part of the formula. And when you're using your book to find their formulas, or if you're using your formula sheet that you have from the book, I guess, just zero that part out. We're never going to use it here. Okay, so now the sigma regarding this is really going to equal P1, Q1 over N1, etc., etc. But instead of doing that, what we have to really do is to get into the bars, P1 bar, PQ bar, all those kind of things, and P bar will be used instead. So we're going to kind of bypass this. We're going to go to what's called a pooled version of the proportion. It's a weighted average of the proportion of successes, P bar. That's what it's called. So it's sort of a pooled version. It's an average version. So that way, if you have big differences in n's, the larger n will win out. So if they're the same, no big deal. You just have 2n. But you find the successes from the first group, x1, successes from the second group, x2. I wouldn't worry about this alternate formula, but it's there just in case you happen to want it. And just get the quantities. We'll always give them to you anyway. And then once you find P bar, you'll have to also get Q bar, piece of cake. Q is always 1 minus P, whether it's got a hat, a tilde, a bar, or even just by itself. So yeah, just go ahead and use that shorter notation. And for reasons that we won't go into now, we will have to take the sum of the reciprocals of the sample sizes down here and add them up. We'll try to give you gentler numbers so you don't have to worry about taking it out to 10 decimal places, hopefully, although it never hurts. Go ahead and find that out, multiply by P bar, multiply by Q bar, and take the square root. That's how it gets kind of be averaged out. So we go back to the example about the percentages of users of the two toothpastes who would never switch. What about the 1% significance level? So we have to be absolutely sure. Can we conclude that the proportion of users of toothpaste A who would never switch is higher than toothpaste B? I don't know. Looks like we had an interval earlier where we had both plus, that is positive values and negative values. Well, let's just take a look. As we've already found, this is just a review, the loyalty percentage for A was 20%. Loyal percentage for B was 17%. And those numbers are exact. We can set up hypotheses, and you do have a choice here. You can put the difference in the p's set equal to 0, the difference in the p's set greater than 0, or if you just prefer, my tablet falls over, to just go ahead and say P1 equals P2, or even P1 is greater than P2, that would be okay. We do not care. It's a little bit faster. It says exactly the same thing. Notice I always use the equal sign in HO. I don't care what the books say. I think it's just easier, and that's a more modern way to do it anyway. Put all the information in H1. Sometimes it's called HA. But yeah, so just go ahead and put the greater than sign, and we will not worry about the less than. That's just embedded inside HO. Okay, everything's greater than 5. Okay, you could double check that if you want. And anyway, both sample sizes are large, which is basically saying the same thing. And yes, of course, we use Z to make the test. And so the greater than sign indicates that the test is right-tailed. The alpha, of course, is 0.01. And from using our table, we could find the 99th percentile and find it's a very large Z. We'd look for 0.9900, as close as we can get to that, on the inside of the table. And reading it on the outside, we would find the Z is 2.33. That's also kind of known as a 98% confidence interval, but I'm not going to go into that because we barely even touched on that this time. Okay, here's the picture. And it shows that you've got 1% in the right tail and a major critical value of Z, ZCV if you wish, to be 2.33. Can you beat it? Can you go larger than that? Then you're in the dark side, the rejection region, where you reject HO. If you can't beat it, then you're not in the rejection region. Notice this is kind of skewed towards keeping HO in place because they have to be absolutely sure in order to overturn HO. So here's some scratch work. I've already tried to make some notation on it. From the 17% and the 20%, the weighted average, the pooled value of P bar is 0.187. That's not a straight up average. That would have been 0.185 if you're looking carefully. But so it's skewed towards the higher total of N. And so a little bit more than that. And go ahead and round that to 3, maybe 4 decimals if you have the stamina for that. Well, anyway, we do take 1 minus 0.87. There's a misprint here. That's going to be 0.83, 0.13 rather. And so 0.187. Okay, I see what happened here. It says there's the error right there. So 1 minus 0.187. This was actually correct. 0.813 is actually correct. I take that back. Anyway, they both go in their spots. The pooled value of P bar is 0.187, and the opposite of that is 0.183. And so then we'll go ahead and put in the reciprocals of the sample sizes. The one sample size was 500, one sample size was 400. At least those are somewhat pleasant numbers, even though they are larger. You'll probably have to take this out to 5 decimals at least, so be prepared to do that. Whereas the S is kind of up to you. I'd say 5 is probably good enough, but they put a bunch in there. So the point is you get a 3% on top, which we already calculated, minus 0, because we always forget about that part, and then divide by hopefully a pretty decent value of S. And when you do, you get a very accurate value of Z, which happens to be way less than the critical value of 2.33. It's pretty much half, but this is exponential, so half really isn't a good analogy. And so it falls in the non-rejection region. We fail to reject the null hypothesis. So we prefer HO. And HO said that it was really about the same. Let's go back and take a quick look at it. Yeah, the P1 is basically the same as P2, at least at the 1% level. Another way to say it, of course, was that the difference was about equal to 0. Okay, so we conclude the proportion of users of toothpaste A who would never switch is not greater than, it's still about the same as the proportion of toothpaste B who also have a loyalty factor who would never switch. So, I don't feel quite that strongly about my toothpaste, but I do use other versions once in a while, whatever the dentist gives me pretty much. So let's go to this example. This organization is a group that defends the interests of the vehicle manufacturers. It released the findings of a study conducted about 5 years ago that included responses to a question that asked people if they can live without a car. That's interesting. Well, more and more, it seems like a lot of us are doing that as we stay at home more than we used to. But this is beside the point. Let's just take it back about 5 years ago. So suppose recently a sample of 1,000 adults from California and then another sample of 1,200 adults from New York were selected. So two different states with two different types of driving patterns. And this is New York State, you'll notice. So I'm sure New York City has part of it, but not all of it. You got upstate, which is completely different than New York City. And these adults were asked if they can live without a vehicle. So 64% of Californians said they could, cannot rather, and 61% from New York said they cannot live without a vehicle. Of course, many people in New York City don't have to deal with vehicles. They deal with taxis, etc. It tests that the proportion of adults from California is different. That's a two-tailed test from the proportion of adults in New York that cannot live without a vehicle. And then they want the 1% significance level again. Okay, so this is looking rather similar to before. Either the p's are equal or the p's are not equal. And yes, if you'd rather just say that P1 is not equal to P2, be my guest. That does not concern me. They are saying exactly the same thing. The original way, though, is more graphable. So if you happen to be graphing, what you're really doing is graphing the first group where you've got the difference of the p's. But I will not care which way you choose to write it up. And when you do a sketch, that tells me you're a way above average student. And so I always look forward to seeing your sketches. Samples are large and independent. We apply the normal distribution. In other words, they all tested out greater than 5. And I'm not going to take the time to do that right now. The not equal to sign in the alternative hypothesis says it's two-tailed, of course, and alpha is 0.01. This is just like a 99% CI, and yeah, plus and minus 2.58 is what we get from that, sometimes known as 2.575. I kind of prefer everybody use the same pattern so I don't have to have too many rubrics, but I'll take it either way. But the point is we do have our critical values as the plus and minus 2.58s. And as you head towards the tails, that's where HO is rejected. In the middle, like a 99% confidence interval, it's not rejected. Okay, so here are some calculations, and step one is always to find the average proportion. And we were already handed, like a silver platter, the proportions from before. So here they didn't really give us the totals, they gave us the percentages. So here, this is where the alternate formula might be helpful. So instead of the x's over the n's, maybe you need to calculate the x's up in front. They're not difficult. I mean, this is 640 here, and this is whatever that is. I don't have that off the top of my head, but it's 600 something. And so you get all that in, divide by the 2200 in the denominator, and you get a weighted average of 0.624. And the complement of that weighted average, known as Q bar, is 0.376. They both go into the formula, and then we multiply by the reciprocals of the sample sizes. Yeah, when you get to the ends being very large, then you have very small decimal places. So I know this one is 0.001, but this one is a little bit, needs to be rounded. You don't want to round too much. So put as many decimals as you can stand when you find you do have to do rounding. Well, our standard deviation does work out to be about 0.0207. And yes, of course, we always subtract that second part of the numerator. So really, it's just the 3% difference, another 3% difference, ironically, divided by the standard denominator, really the standard error, I'll just say S. And then we get a Z of 1.45, which does look kind of moderate, especially since we had a pretty high bar to cross. And we're in the non-rejection region. We weren't anywhere near the plus and minus 2.58 that you can find if you go back a couple of slides. And so, yeah, we're going to, once again, fail to reject the null hypothesis. In other words, they're about the same. They're not different. The official way is to say that they're not different, but what else is there to say? But they're about the same. And we're not going to say they're exactly the same, but we cannot say they're different. That's for sure. Yeah, and that means they're roughly the same, especially at that strict level, alpha 0.01 two-tail, of giving us a Z of 2.58. We weren't even close to crossing the line there. And yes, one could find p-values for that and see that it beats the 0.01, but I'm not leaning in that direction. That's up to you if you're using technology, or if you just like to use the tables with Z to go ahead and do. But then you just try to see if you can beat alpha. And we've explained that one already. Now here's a little note to many of you. I assume you're using a table, which of course is indicated by 4 decimal places. Unless you provide calculator steps, then you can provide how many decimals you want. But once again, I do want steps. And if you're going to take the shortcut by using a calculator, I don't mind if you fill me in as to what you're doing. And so many students just hate that. I just don't understand that. But if you show me your steps, then congratulations, you saved yourself a heck of a lot of time, assuming you did it correctly, that is. So otherwise, for most of you, I assume you're using a table. And it's the strangest thing on the quizzes. I've been seeing a lot of people with 5, 6 decimal places. I know you didn't get that from a table. And I'm not saying you have to use a table. And on a quiz, there's a little less work to be shown, at least in the beginning. We want you to show more work now at the end. But yeah, you should be using the calculator steps if you're giving me more than 4 decimals. So, take a clue here and, do one way or the other, but not both. You can't straddle the line between the both because you will not hit either one of my rubrics and you will lose points because there's often different answers for the different methods. And so if you pick a hybrid method, oops, I guess you fell between the cracks and won't have enough time to save you, I'm afraid. So anyway, these are just examples of some of the ones that we ran through earlier. So you can take a look at them. These are all found in the back of your book. They all start with stats tests. And so I'm just going through these kind of quickly. And now let's go to the 2 sample t-tests for proportions. Some of these are a bit of a review. Sorry about this chicken scratches on the bottom of the screen. But just to kind of quickly go through the review here, samples need to be randomly selected. They can't be cherry-picked. The samples should be independent. Samples must be large enough to use a norming sampling distribution. And yes, of course, all those items have to be greater than 5. And so if the conditions are met, then the sampling distribution for P1 hat minus P2 hat is normal, and the mean is just exactly what you think it is. Just take your hats off and subtract. We need a weighted estimate, pooled estimate, and yes, the typical way is just to add the x's, divide by the sum of the n's. And here's the standard error, the standard deviation of the difference. And notice it uses the P bar and the Q bar, so this is just a review before, nothing big. And so we have the 2 sample z-test, and they're going through the checklist again that we talked about before, and all these have to be greater than 5. Test statistic is the difference in the P hats. And here comes Z. Z takes the difference in the P hats. We just did this just a few minutes ago, so if you're going faster through this, I don't blame you. But if you did pause it and want to see it again, this is a slightly different version of the same message. So we're going through the step-by-step stuff. We get the P bar, we get the Q bar by subtracting P bar from 1. And find HO, find HA. I always put HO having the equal sign. I encourage you to do the same, make your life easier on yourself. And I don't ask the heavy questions that actually require you to think about that to a great extent. H1 is what we typically use, but HA, we understand what HA means. I don't really care which one you use. We have to identify alpha. They've already identified it for you. You won't have to do that yourself. And find the critical values from the table. And when Z is being used, like now, they're very cut and dried. Most of the time, they're about the same ones over and over again. Unless they're one-tail tests, then maybe you would have to look up a 2.33, something along those lines. Find the rejection regions. Of course, if you've given me a sketch, then you've already done that. So I always prefer a sketch, whether it's 2-tail or 1-tail or whatever. You can shade in the dark side. The standard way of going is the dark side is always where you reject HO. That's the critical region. If it's lighter, then you don't reject HO. That's just that simple. And yes, we have the formula again, so a lot of this is reviews. Let me quickly go through this so we have time to review for our final. Make a decision, interpret the decision, and be prepared to defend your case by giving me a half a sentence of what happened. What was your favorite hypothesis? What does it say? That kind of thing. Okay, so here's a good example. A study of 200 randomly selected occupants in passenger cars and 250 occupants in trucks shows that 91% of occupants in cars and 83.2% of occupants in the trucks wore seatbelts. So I'm not sure when this was taken or what state it was taken in. Alpha is 0.10, so we've got a big margin there for us. And can we reject the claim that the proportion of occupants who wear seatbelts is the same for cars versus trucks? Can we reject that? In other words, is it different? So we're looking at equals versus not equals. It's just that simple. Okay, so we have some data. They summarize the data, which is always nice. You can do the same if it isn't done for you already. So let's take a look. Samples are random and independent. Weighted estimate would be in between the two numbers. Remember, we had 0.910 and 0.832, which is a weighted average, works out to be 0.8667. 4 decimals certainly doesn't hurt. We find Q bar as well. I suppose we could get by with 3 decimals here, I imagine, so that would not be a serious issue. They've done the checking here. All those N1 P bars, N1 Q bars, and 2 P bars, and 2 Q bars are all greater than 5, or at least 5. You could have it equal to 5, I suppose, in this addition. You could use the 2 sample Z test. Let's get started with that. They say the claim of the proportion of the occupants that wear the seatbelts is the same, and they have not offered a direction. So by default, it's either the same or not the same. Two-tailed is the default position. If you don't see a direction, don't put one in there. Just make it two-tail. And then this, of course, is two-tail, and this is like a 90% confidence interval. It's just very, very close to that, just looking at a different angle on it. And so our Z's are just what you might expect. This addition does give us 3 decimals. So if you'd rather just use plus or minus 1.65, we'll certainly take that. 1.64 is a little off, so we don't prefer that one, though. The rejection regions are heading towards the tails, as you might expect. So we find out what our test statistic of Z is. And after we've jumped through all the hoops, and we find the difference of the two, which is what, 7.6%, 0.076. That one's easy. But then the denominator, a little bit tougher. We have some relatively friendly ends to deal with, 1 over 200, 1 over 250. Those are actually nice exact numbers. So those are something I might even use on the test, who knows? So you don't have to round those. And then you put in your P bar and your Q bar. 4 decimals is better than 3, but if you don't have time for 3, we'll understand. And so you get a decent value of Z, and that looks like it's a pretty strong one. And it is, because we beat the outer limit of the higher side Z. They call it Z0 here. And we beat it. We got 2.42. We landed on the dark side, and we're rejecting the null hypothesis. In other words, we do prefer H1, where we did show a difference. So the H1, recall, was getting into where the point was that they were not the same proportion. Didn't say that one was greater than the other. We just said they were different. So there's a big difference there. Because if you're one of those crusade to make everybody wear their seatbelts, which there's nothing wrong with that. But we can't say that one is greater. We just simply say that the two are different. And that's quite important to say that, because that's a very heavily misused way of interpreting things. So we reject the claim that the proportion of occupants is the same. It is different, as we said. Okay, so another one. Here we have a medical research team conducting a study to test the effects of a cholesterol-reducing medication. And so we found that of the 4,700 selected subjects who took the medication, 301 died of heart disease. Wow. But out of 4,300 randomly selected subjects who took a placebo, 357 died of heart disease. They've calculated the percentages. They didn't show the work, but with the medication, it looks like it's about 6.4%. Without the medication, with only a placebo, it was 8.3%. I do see a difference of almost 2%, but can we say that the death rate due to heart disease is lower for those that took the medication or not? This is a one-tail test, a left-tail test. So yes, we find the average P hat, the average proportion overall of the 9,000 people involved in this long experiment, I'm sure. It works out to be a little more than 7%. We get the complement, of course, for the formula around 92.7%. And so we do the double checking if you have time. This is probably the least important aspect. If you nail everything else, I'm not really worried about this. But if you're just preparing for possible difficulties, this does give you some kind of in lieu of type credit. I'll put it that way. I don't want to call it extra credit. Okay, so let's see. We do have a one-tail test. Notice how I've heavily shaded in the less than sign right there. It is lower. And yeah, if you really have to say greater than or equal to on the HO, I don't mind. It's just, if you stew about it and waste time over it, then you really missed my message. I just say put an equal sign in and just don't worry about it. So we have a less than situation, a left-tail test, and this is left-tailed, alpha is 0.01, and this critical value is a negative 2.33. It's a Z, and it's easily found if you just look in the table for numbers. You can get as close to 0.0100. This is the first percentile, also known as P1, capital P1. So if we get it less than minus 2.33, we've rejected it. Let's just see what we got. And we do get a negative numerator, and our denominator is always positive. It has to be. It's a square root. We only have real numbers here, of course. So that means we have a negative 3.46. That is a very strong negative number. We have crawled over onto the dark side, it looks like, and we have found that it is lower. So there it is, minus 3.46 is indeed further over than the minus 2.33, which is like what I call the line in the sand. And we crossed over to the dark side, so to speak, all these analogies. And so now we do have the fact that P1 is less than P2. So the medication does seem to be working. It isn't perfect, but it is better than a placebo. That 1.9% difference was enough, and especially with 9,000 people total in the survey. Yeah, we can really see it. So yes, it is lower for those that took the medication versus those that took the placebo, 1% level. Okay, so now let's see if we can go through a few problems for our test. And I've taken a look at a couple of older finals that I'm not really reusing. And I'm going to try to do at least one problem from every chapter. Starting at 6.3 is the second half of the class. So that's where the homework is due, 6.3 through 10.5. Skipping the sections we didn't cover, and that's what's going to be due right around the day of the final. So as long as you get that submitted in a timely way, I'm not going to say anything, but I'd have to say that Thursday the 11th by, say, midnight is probably what I'm going to put down. And really don't go much longer than that, because I've got very short time to turn around the tests, and I won't be able to really search for homework. So you really need to make sure it's downloaded, hopefully on Blackboard, and if not, send it by email. No zip files, make sure it's PDF or JPEG. Put the pages in order, please, because if I find it's all scattered in 20 pieces, you're going to be graded last, and there may not even be time, so you might not get credit. And the homework is about 6% of the grade each time, so that's a lot of points to throw out. You don't want to do that, and I think it's far more important than web work. Okay, let's take a look at a problem from number 3. Number 3 had several different examples. It had Chebyshev, and it had coefficient of variation and a few other things, but I think I pledged before I wasn't going to do any more standard deviation problems. We did probably too many of those on the midterm, and we're trying to keep this mostly on Blackboard as much as we can. So let's take a look at a coefficient of variation problem, and I still like you, if you can, to write down the formulas, whether it's the handwritten version that's downloaded or whether it's just on Blackboard. If you want to try just on Blackboard, that's a slight risk. But anyway, the formula looks like it would be S over X bar times 100%. There is a population version. So we have salaries that have a mean of 62,350, and that was a X bar, 63,250. It had a standard deviation, S, of 6820. And these are salaries, so they're dollars, of course. And we also have experience. We had a mean of 15 years for this company, and the standard deviation was 2. So this is the salary. Just put a dollar sign, and we'll say the years, YRS. Which one is more variable? Which has the highest relative variation? So the idea is to go ahead and calculate them out. And so the first one for the salary would equal the ratio of the standard deviation over the X bar. So this looks like a pretty simple problem. If I happen to give you something like this, I think everybody should clean up on this stuff, assuming you know how to use a calculator at all. And yes, this is one of those that has to be put in a percentage, because they did say coefficient of variation. This is a percentage answer. Sorry, I can't do anything about it. That's just the way they decided to do it. So a decimal here, you would lose some credit. So that has a variability of going on 11%, whereas the years, a little bit easier to calculate. You get just 2 over 15 times 100%, that is, which yields 13.33%. So I picked 2 decimals. Pick the same level of rounding. That's something I look for. Please pick the same level. If you pick 2 decimals in your percent, please use 2 decimals in your percent. Be consistent, or points can come off. So don't fall into that trap. So yeah, looks like the years were more variable. So more variation. I don't write very clearly on this tilted screen, but that's the best I can do. So that is one problem for you. Chapter 4, it seems like some of the better problems had tables. So maybe I can put down part of a table for you for chapter 4. That was chapter 3. And we had one of those in your midterm. So I would say study that carefully. A lot of people miss the ones towards the end a lot. You shouldn't be multiplying any probabilities because if you look at the rule, it says that they're independent. Well, if they're not independent, why are you multiplying? And these tables are almost never independent. There was one about the sugar in the coffee or something like that by gender. It turned out that they were the same. They were independent, but that's rare. You're not going to see that on the final. So, yeah, just go ahead and take a look at the individual probabilities. That's the smart move. So let's see if we can do this quickly. I don't want to waste all day. So we had male versus female and whether they've ever shopped online. So yes, shopped online. No, never shopped online. And so we have some totals that might be slightly out of date because it seems like everybody shops online nowadays. But 500 versus 300 on the yes versus gender, and then 700 versus 500 for the no. Quite a bit more no's on that. And so, yeah, you can get the subtotals. We figure you can do that yourself. And then we can ask various questions. How about some conditional probabilities? How about probability that it's a yes, so shopped, given that it's a female. So that's how it's written. Yes, given female. So now let's find out how many total females there are. And we would see that there are, let's see, male versus female. That would be 300 plus the 500. So given that it's a female means that we only have the 800 females to look at. And that goes straight in our denominator. And then we look at those that said, yes, I have, and that's 300 over 800. Please give me a decimal. Now, frankly, this one could be a rare exception. It's a simple fraction. But, yeah, there are some people that just don't know how to use their calculator to get decimals. And I'd rather see a decimal, round to 3 or 4 decimals. This one's exactly 3 decimals, as it turns out. So that kind of thing could be done. Let's see. What about... okay, let's do another conditional. That's the ones that people have more trouble with. So how about the probability that we have a male given that they haven't shopped? So male given a no. So the no actually goes first. It's kind of written backwards. So we only look at the no's. That column is all we care about. And there's a total of 1,200 no's. So just look at the rows or columns and then throw everything else away. So we got all the no's there. How many of them are males? 700 of them. Take a look in the corner. 7/12, also kind of a borderline simple fraction, but we'd rather you go ahead and tell me it's 0.583 or 0.5833, and that would be just fine. And just play around. Make sure you understand the problem from the midterm and other problems similar to that from the tables. I don't go into some of the picky uni things in Chapter 4, but I think the tables are there's a lot of stuff in the tables. And in fact, I had a teacher at UCR that wrote the book literally on the information found in tables like this. And yeah, he also had a last name with about 20 letters in it because he was from India. But he was a really nice guy, one of my favorite teachers, definitely my favorite teacher at UCR. And he knew all there was to know about tables. But anyway, I think that's the core of Chapter 4. Let's move on to Chapter 5 and see if I can find an old problem that might be some use to you. And let's see, what about a binomial? You can't skip binomial. That's one of the most important distributions of all. So as I go to Chapter 5, and maybe I'll change colors on the next slide. They're saying, according to a survey, 45% of drivers say they exceed the speed limit. So we can just start off with P equals 0.45. And of course, Q is 0.55. I hope that's a no-brainer. That should be very easy. Then they're saying a random sample of 10 drivers is selected. So N is 10. Find the probability that the number of drivers in the sample who do this is at least 8. Yes, we assume that everybody knows what at least means. I'm old enough to remember where everybody actually remembered that. Now I've noticed quite a bit of slippage on that, but at least is 8 at the minimum. That means 8, 9, or 10. That's all it is, nothing more. Don't head off to being less than 8 or some crazy thing like that. It's 8, 9, or 10. So yes, there'd be 3 separate calculations here, unless of course you're using a calculator and show me the steps, which would be perfectly okay. I'm not going to demand a formula here if you show me the calculator steps. Otherwise, I do need a formula. I do need some steps, and it will take a little bit longer if I ask for a 3-parter. I could just ask for a couple or even just one. So, keep that in mind. Obviously, you have your formula, and I'll assume you could look up the formula. Let's just start off with 8. So P of 8 would be 10C8 times 0.45, which is the value of p, raised to the 8th power, then the value of q raised to the 10 minus 8, which of course is squared. It's always nice to put the subtotals in if you have time, but you should get something like 0.02289. And then you can go ahead and find p of 9 similarly with the formula. And that one happened to equal 0.00416. P of 10, they'll fit on here, was equal to a very small number. It's really hard to get all 10 of them correct when you only have a 45% of chance of success to get 10 in a row. So if your free throw shooting ability is only 45%, which means you never make the pros, and to get 10 in a row is not impossible, but it only happened 3 out of every 10,000 instances of when you have to shoot 10 free throws. So I wouldn't hold your breath on that one. And you add that all up, and you do get about a 0.0274. Just for trivia purposes. Let's go on to another problem, and I'll move on to another slide here. Let's go over to chapter 6. That's kind of where we left off, and I feel that the final should be roughly 2/3 to 1/3 as far as starting at 6.3. That's where you have a higher percentage of problems from sections. Of course, I can't cover every section, but I will cover every chapter. I really try and go out of my way to cover every chapter somewhere on the final. So let's take a look at problem number 8 that I had from my old final, and let's see what this one has. This one has to do with a, well, let's go to 6 point, yeah, I'll try that one, number 4 instead. Yeah, 4 is probably a little bit better. Let's do that one. Okay, here a baseball pitcher has his times between pitches averaging 36 seconds. So for chapter 6, U is 36 seconds. I don't know how that compares to the league average. I really don't know. But we do have the standard deviation is 2.5 seconds. So that is a 36. And sigma is 2.5 in terms of seconds. And what proportion of his times between pitches are between 29 and 34? So we could say that your x would be between 29 and 34. And don't have to put an equal sign on that. But calculating the z's, the most important formula of all, hands down, is z equals x minus mu over sigma. We see several versions of that, and t looks suspiciously the same as this. So let's start with the first one. 29 minus 36, which is 7 seconds below average, divided by 2.5 gives us a z of minus 2.8. 0, because z gets 2 decimals. Now, if it's exact and there's a 0 on, I don't usually care about that. But if you're using the table, why the heck are you putting more than 2 decimals down? You're just asking to be confused. So that's why I always say use 2 decimals for z. Calculator users, I'm not talking to you. But table users, which is most of you, I am talking to you. So please, 2 decimals. That's important. Otherwise, unless you can round in your head quickly, and some people can, and that's not a problem, but a lot of people don't. They just misread it, and then the points start falling off like rain. So what can I tell you? The other z value gets you 34 minus 36, because both of these numbers were faster than average, and that z is minus 0.80 or 0.80. So then you look up the probabilities, and yes, a sketch is always handy. I put the mean down just for reference, but both these values are less than the mean. So you've got your typical x values between 29 and 36, and for reference, 34, and then the mean over there was 36. So anyway, you get your cumulative probabilities and subtract them away. You get 0.2119 minus 0.0026. That other one was rather hard to do, but the difference is 0.2093. This is what I consider a bellwether problem, a fundamental problem. When people miss this kind of problem, it tells me they really didn't learn the class very well, because this is kind of a cornerstone type of problem. So yeah, of course, these types of problems are on the test. How could they not be? So if you still have trouble with it, spend some time and learn it. This is vitally important, because a lot of other stuff is built on this. Indirectly or directly, it's just cornerstone on this. We have normal approximation to the binomial, so you should be able to do that. Let's see if I can get a quick example here, at least a portion of an example. That's proportions. So I wanted to get my notes together here for problem number 8. Yeah, so we have that one is a little harder to find. And yeah, normal approximation found in 6.5 is especially valuable with larger numbers that the calculator cannot get. And so let's just see if we can do part of this. This is 6.5 normal approximation. And they're saying that 61% of people support red light cameras at intersections. So we can just start off with P equals 0.61. Q, of course, is 0.39. And we have a sample of 800, pretty healthy one. And we want to find the probability that at least 520 support the cameras. But because this is a normal approximation, this really means that X is going to be greater than 519.5. All the numbers that round into 520, just like the Riemann sums in calculus, which you've all had, is a very similar idea where we're trying to fit the rectangles into the curve. It's an approximation. It's almost always a very good one, and in lieu of trying to find a high-capacity computer that may not be available, this will do, because it's almost always within 1% of the actual answer and quite a bit easier to do if you know what you're doing. So if you're caught in a pinch, this approximation can save you. It's almost never further off from the actual answer by more than 1%. It's always quite close. There are rare exceptions, of course. So anyway, here you'd have to calculate mu. And mu is n times p. It's a lousy looking mu, I'll tell you. So n times p, that happens to be 800 times 0.61. When you multiply these two numbers together, you do get 488. So just to kind of wind things up a little bit, z now would equal x minus mu over sigma, but we could replace the mu by np, and you could replace the sigma by square root of npq. And if you do that, you'll get 519.5 minus 488 divided by what would work out to be 13.796. And that gives you a z, which you should be pretty close to. I'll accept a little bit of slippage, but if you give me at least 3 decimals everywhere, 4 decimals everywhere, then I consider that to be a good faith attempt. Of course, if you're using the TI, you don't even have to worry about it. You'll give me the exact answer anyway. So anyway, when you look for that kind of thing, and here comes the required sketch, it's going to be one of those we're kind of aiming at a high number. If the mean was 488, we're looking for a number that's more than 520. Of course, this is a right tail calculation. That's not a hypothesis test. But we're looking for something greater than 2.28 on the z-scale. So if you're using your table, it's going to be 1 minus a particular value. And remember, there is a difference between probability and z's. On the quizzes, some people can't tell the difference. But yeah, p, which is the probability, will be 1 minus the 0.987887, which is over here, which doesn't leave very much. This is going to be kind of hard to do. We're going to get about 1% of the time for this one, 0.0113. That's how that one ends. Let's move to Chapter 7 and take a look at a couple things here. So that would be problem number 10. And this one has to do with proportions. And they're saying that 83% of orders at a distributor received from customers arrive on time. So on-time percentage of 83. I think we saw an 85 earlier. Let p hat be the proportion of orders in a random sample of 100 that arrive on time. Find the probability that p would be less than 0.89. So let's skip ahead to another slide. I'll do that right now. Let me put down some information for you. So p does start off as 83%. N is 100. NP, by the way, is greater than 5. Yeah, that's nice to know. NP is 83. I'll just tell you that visually. And NQ, because Q is 0.17, quite obviously, 17 times 100 is also 17. Yeah, they're both greater than 5, so I just verbalized that one. So we're wanting to find the probability that the X bar, you could say, but I'm going to go ahead and say that the P, little p, is from the sample, that is, p hat would be less than 0.89. So less than 0.89. So let's see what that might look like on a curve. If they're telling us that 83% is the average, to be less than 0.89 looks like it's going to happen a lot just based on what I see here, and I'll lightly shade in. The big portion here is clearly more than half of the curve, and it could be quite a bit more than that. So the question is, how do we get z? Well, z using the proportion formula, it still has the same structure as before, but we'll start off with x being replaced by p hat. We'll start off with mu being replaced by the actual p, and this is p hat over here, so I need to make that clear. And that's divided by the standard error, which happens to be PQ over N. So you'll be able to look that up quickly or have it on that note sheet, the blue note sheet that comes in your book. And so we'll go ahead and subtract that out and get 0.89 for what our cutoff value is for the request. And then we subtract 0.81 from that, divide by a number that does work out to be about 0.037563. More decimals, the better. Let's see, actually we divide that out, and let's see, we got 83%. No wonder. Yeah, that's my fault. I apologize. Yes, that's it. 0.83 for P. Yep, right there. So our Z works out to be kind of moderate. It's 1.60. But the question is, what's that probability going to be? So this is directly from the table. Couldn't be easier if you're using a table. We simply look it up, and the probability, just using the left-facing table, notice our information is facing left. We just look it up, and it's going to be pretty likely 0.9452. That is a 4, and that would be your answer. The twist is the proportion. Otherwise, it's quite similar to what we've already done, and that's a Chapter 7 problem. Let's look at Chapter 8. Let's get one of those where we have to solve for a sample size. We haven't done that yet, so let's see if we can take care of that. I'll look for number 13. Let's find the minimum sample size for Chapter 8. Just did a Chapter 7 problem. Keep in mind, these are only selections. There are many others that are available, and I don't always pick exactly the same problems on the final, obviously, but these are good representative problems for which you may see again. And certainly, your written homework is a good judge for that. So minimum sample size, the margin of error of estimate for a 95% confidence interval. So we want to find N. I'll circle that. 95% CI for P. And we say that margin of error is 0.024. So we'll just say capital E, which is what your book is using, is 0.024. But because we have a 95% CI, we have the ultra-popular Z equaling 1.96. That one, hands down, is the most popular number we have in all of statistics. Hope you memorize it. It also means alpha is 0.05, another way of saying it. Okay, so that's your idea. And N is equal to P hat Q hat times what I say is just Z over E squared. Make it a little bit easier on yourself. And we did have a prior estimate where P hat was 0.35. So if this is given to you, or you gather that from the reading the information, then all we have to do is say that N is 0.35 for P hat, 0.65 for Q hat, Z is 1.96, and E is 0.024. And yeah, occasionally you do get an exact number where you don't have to round it up, but this isn't one of them. This happens to be 1517.3, which is really 1518. I'll be looking to see that you can round up here. Mostly normal rounding rules apply. 0 to 4 round down, 5 to 9 round up, but not here. If there's any decimal at all, you round up because they did say minimum sample size N. And by the way, if it was 50-50, if they didn't give you any information, so no survey, no prior information, or they just simply leave it blank, which is tough for a lot of students, if there's no info or limited info, or they just flat out say we don't have a prior survey, then P hat is equal to 0.5, which of course is the same thing as Q hat. That always drives your N up. Unfortunately, that means you have 0.5 times 0.5 times the rest of it, same as before. And that changes matters. And then you get to 1667.4, which of course rounds up to 1668. That's an extra 150. That's the penalty you pay for not having a prior survey. So anyway, let's move on to another one. That was Chapter 8. How about another one from Chapter 8? Let me see if I can find that one over here. Here's just a mere confidence interval. Most people find confidence intervals easier than hypothesis testing. So let's do a confidence interval for this one from section 8.3. Let me just put down the formula first. I personally feel that a formula is your roadmap. for what you're doing and for what I'm trying to follow what you're doing. And those that don't give me a roadmap are leaving me in the dark. They're turning the lights off and saying, oh, it's midnight, and good luck. And, I don't feel so good about it most of the time. So anyway, get in the habit of doing that. And they're saying that we have a random sample of 41 cars. N is 41. There's a mean, and from the sample, it's a sample mean, of course, X bar is 26.4 miles per gallon. So MPG, you could indicate that if you want to. And the standard deviation, which of course is S because it's from a sample, and they didn't say anything else, that's 2.3. Then it should just be a plug-in, although in this case you do have to look up the value of T. So with a 99% confidence interval, you would have to look, and I will give you a heading for that is a table, the T table that will have headings that talk about confidence intervals. I encourage you to use that. If not, you'll have to figure it out by hand. There was a method the book talked about. You can do it the slow way if you want. I'll just provide you the easier table. So anyway, T does work out from the 99% confidence interval, that is a 9, along with how many degrees of freedom? DF is 40. So you're looking at 99% CI, comma 40. That's notation. That's perfectly okay. And you would find, and T always gets 3 decimals, so listed as 2.704. And now we can just do an easy plug-in. And if it's Z, it's even easier, because Z usually hits the buttons you've seen before, the 3 values. But in this particular case, you got your 20, oops, let's go back. I don't know how that happened, but we have 26.4. If I touch the screen, crazy things happen. So T is 2.704. This should be routine for many of you. There's your 2.3 for the S, and we divide by the square root of 41. And then you'll get 26.4 plus or minus 0.97. And then please finish it off by adding and subtracting the numbers. We do want you to do that. So then you would get 25.43 up through 27.37. And the algebraic notation is faster, so we encourage you to use it. Of course, you do have to use the parentheses and the comma, or credit is not given. Or you could use the inequalities with the less than signs if you want, or just even use English and use the word TO in between the 2 numbers. Always lead off with the smaller number first and the larger number second. Keep the same level of rounding. Don't give me 1 decimal here and 6 decimals there. It just looks unprofessional. So leave it the same. I don't care what level you pick. 2's good, but make sure it's the same. Even if zeros are at the end, that's perfectly fine. In fact, it's expected. So that's part of Chapter 8, and there's many more things in Chapter 8. Let's go to Chapter 9. I'll look at problem 14 from the other test. See what I can come up with on this one. Hypothesis testing involving proportions. This is from 9.4. And hypothesis testing is a major part of this class. You should expect to see it on the final a few times, 2 or 3 times or so. According to the Census Bureau, 62% of adults in the U.S. are married. A new random sample of 2,000 adults showed that 58% were married from this sample. So let's start off with what they told us. They said that the proportion was 62%. So I'll just start off with P equaling 62%. Now, can you reject the null hypothesis in favor of the alternative that the percentage is lower than 62%? Lower is a less than type of experience, so please put the less than sign. Everything else is the same. So that makes it hopefully easier. Don't worry about anything but an equal sign up in HO. That's my advice to you. Always put an equal sign there. Okay, so we've been finding that the p hat is only 58%. And we had a pretty decent sample size of 2,000, I'm sorry. Yeah, NP is good here. That's greater than 5. So let's break out a formula for Z, and let's see what we get. The value we get, well, I like to call Z sub data, because there's no doubt where that came from. That's the way I learned it anyway. P hat minus P divided by the standard error, PQ over N. Notice that's a large radical. It should be written that way. Otherwise, errors do occur because people forget what formula it is. This is off by 4%. It's on the low side. So yes, that is a negative 4%. And yeah, that fits the less than indicator there. So perfectly okay. Let's divide by no hats, PQ over N. So we have to go right to the P of 0.62. And we figure that Q should be easy. If you need a calculator, please use it. You may not need one for something this simple. It's 0.38. That's part of the formula. And n, of course, is 2,000. That's going to really shrink that standard error down. And that becomes like a 0.0108 and change. More decimals is good. I'll put an extra 5 in there because that would round to a different number. So now we get a rather strong value of z, a minus 3.69. Now I did not list the line in the sand. I should have done that first. I just can't wait to find out what the data value of z is. That one already looks pretty far over to the left. But let's lay down the line in the sand. Here, as I finally tell you what alpha is 0.01, and we did see this one a couple of times recently, where the critical value of z, call that z0, zcv, minus 2.33. And yes, we landed way over on the dark side there at minus 3.69. So the option here, and the sketch makes it ultra clear. We reject HO, to say it more formally, or if you'd like to just prefer H1, that's okay too. What we're really getting to, if you have to comment on this, is the P does look like it's less than 62%. The difference of 4% doesn't sound that much, but we've got 2,000 in this sample. That carries a lot of weight. That pulled that Z way over, pretty much off the table. So if you're trying to get a p-value from a table here, I guess you just have to call it roughly 0, because I'm going to try to avoid z's that fall off the table. So that's another problem from number 9. Let's see if we can find a couple from chapter 10 and kind of round it out. Let's see here. Let's do a confidence interval, which most people find to be a little bit easier, but it does have the two things going on, so we do have to be careful here. First of all, we do see that it's from 2 independent samples selected from 2 populations. So let me just go ahead and list the summary statistics. This is from section 10.1. And so we have the first sample has 650 in it. And we have an average from the sample found to be 1.54. However, the standard deviation is even larger than that. That's a little peculiar. Then we go to the second sample, 675, and that average is 1.05. So that's the core of it right there. This part right here, that difference, is that going to be significant or not? Well, the confidence interval doesn't directly answer that, but we do look at it. And here, once again, a pretty wide standard deviation, 4.8, 4.80. Okay, so here's the formula for the confidence interval. We're going to be looking for a 95% confidence interval. So CI. And here's the formula. First of all, we subtract the sample means. You may bundle that together in parentheses if you wish. That's up to you. We add and subtract the special value of Z. In this case, it's going to be 1.96, the ultra-familiar number. And then we multiply by the sigmas, which are actually given here. The sigmas allow us to use Z. That's good news. So in the real world, it's a bit uncommon, but we do have it here. So that's going to be what they call the variance, sigma 1 squared. We go ahead and add in the other variance, sigma 2 squared, and divide by the sample size. So there's a lot of plugging in on these. If you have a calculator, TI type calculator, show me your steps, save some time. But without the steps, you're wasting everybody's time. So I hope I made that clear by now. 1.54 minus 1.05 does yield a difference of 0.49. So that's like our center point. So we put in the previously stated 1.96 for the Z. We can put in the rest of the numbers too. Be prepared to jot a couple numbers down or use some memories in your calculator, or use lots of parentheses. I don't care how you do it, but you shouldn't be rounding too much or you may have a serious problem with your answer. I'll just plug in the numbers as I see them. 4.8, I'll just drop the 0 here for scratch work, and we just go ahead and calculate all that. I will not show you all the details there, but it does work out to be something as close as you can get to 0.223796. I did that as exact as I possibly could, and I double-checked it on the TI, and it worked out all right. So now we get a margin of error of 0.439. It's typically preferable to go one extra digit beyond what was given. So I'll put that extra 0 in just to show you. The margin error is pretty big. So when you subtract it, we still have a number just above 0 at 0.51. You add it, you get to a very wide number, 0.929. So we have, these are not proportions. They're not anything to do with percentages. They don't even say what these units are. But the confidence interval was, by the way, for the difference in the means. I didn't make that especially clear, but yes, we use the X bars to pitch hit for the means, and then our interval is between those two numbers as you see on your screen. I noticed, though, that they're all greater than 0. And a hypothesis test, a two-tailed hypothesis test, would have no trouble staying above 0, saying that the population of X1 is greater than the population of X2. In other words, one could easily turn this around. We're not doing it right here, but it also has to be that mu1 is greater than mu2 as a side effect of all this. But anyway, that's the confidence interval. Lots of plugging in, but in general, confidence intervals are somewhat easier than hypothesis testing because basically it's just a matter of doing all the plugging in you can and trying not to round too much. Let's go over to another problem and look at another t-distribution. I know that's one that's a little less familiar to a lot of you. So here we have two more populations. This is going to be from 10.3. And so here, the following information was obtained from two independent samples selected for populations with unknown standard deviations and assumed to be unequal standard deviations as well, because how would we know they're equal? That's a separate process, which we're going to avoid. 10.2 we're not covering this time. Did cover it the past few years, but not covering it now. Proportions are more important in the long run. So here we have mu1 minus mu2 equals 0, or they're just the same if you rather just say it that way. And here with a two-tailed test, we'll look at the difference not being equal to 0. So there's the shorter way of saying it if you'd rather do that. I don't much care. So here comes the data, and let's provide that right now. The first sample size is only 14 with a mean of 109.43 and the standard deviation of 2.26. Now the second sample size is also small. It's only 15. The average mean, which is the core of this, is 113.88. So right away you can see there's a difference of around 4. You can tell by subtracting the two numbers that's around 4. Maybe it's negative 4 the way it's set up. So the standard deviation here, which has something to do with it, is going to be 5.84. So these clearly are different standard deviations. They're nowhere near the same. And if they were the same, you would get to take a shortcut. We're just not going to waste our time with that. So just assume the worst and you're good. Alpha is 0.05. And degrees of freedom is 18. I encourage you to use the degrees of freedom to be the smaller sample size minus 1. Do not use the DF formula. If you're clearly using a TI, and the way I can tell is because you're showing me your TI steps, then you may get a slightly different answer. But for somebody to try that DF formula by hand is a pure waste of time. Don't do it. You're going to waste a lot of time. It's not going to improve your answer at all. In fact, it's just going to slightly confuse me. So we had, well, okay, actually, I take this back. You could have easily used 13. Because 14, the smaller sample size, is subtracted from 1. But the way this problem was set up was, I take back what I just said a little bit here, they had already used the formula or found it from the TI calculator to the nearest unit. That was 18. So this is just a given. And we could do the same thing. We could just avoid the topic altogether by giving you the degrees of freedom. If so, please take it. So if it's not given, I would use 13. Unless your TI gives you something else. Then you can make a note of that, and I'll have a rubric for you for those of you who are using the TI. So let's use 18, and let's go to the formula. T will be given to be the difference in the sample means minus 0. Don't even have to worry about that. It's just not a problem for us. And we have to divide by the standard error, which is in terms of the S's. After all, we have the T distribution. That means sigma is nowhere to be found. That's the whole reason we have T, is when sigma goes away and S replaces it, then T has to replace Z. That's just the way it is. Unless, of course, N is very, very large. Then exceptions can be made, but we're not seeing those. So we have that kind of situation, and then we can carefully plug in some values. And we see the difference of the two values, the 109.43 and the 113.88. I'll just go ahead and tell you, you can check my work. That's a minus 4.45 in the numerator. It is a negative number, but it's still a two-tailed test. Notice that is a not equal to sign over there. And so then we plug in all those other numbers and we get 1.624. And as many decimals as you care to show me, I'll just go ahead and list a few extras for you. T does go to 3 decimals, so you may want to be a little bit more careful with the T. We get a minus 2.740, 3 decimals for Z, of course. And so now, what does that mean with regards to testing our hypotheses? So perhaps a better way is to list the critical values. We've already got our end result, but what were the critical values here? TCV, so to speak, would be T with 18 degrees of freedom and 0.05, of course, with 2 tails. So look for the headings. Either it's 1 tail, 2 tail, or confidence interval. So this is a 2 tail scenario. And that means our critical values from our table, and we do a plus and minus because there's sort of an invisible left side too, plus or minus 2.101. A sketch is always appreciated. And we could list the values here, 2.101 minus 2.101. And yes, we found that we landed into the dark side at 2.740. We reject HO. We prefer HA, if you want to say it that way, H1. You can say that if you want. But meanwhile, go into the one that you are kind of liking. You prefer the fact that mu1 minus mu2 is not equal to 0. In other words, to sum it up, we could just simply say that the means are different. That's directly implied here. So we prefer the fact that the means are actually different. And that unit 4 unit difference, 4.5 unit difference, did stand up to the scrutiny. Didn't look like much. We didn't have very big sample sizes, and it's just the way it shook out. It was a kind of a close call. We do not expect p-values here. If you have a TI and you insist on a p-value, I guess I'll take it. But the standard way here would be to compare critical values. So as I said before, if you never use a p-value in this class on the test, that's okay with me, because so much of it without technology, especially with the T's, has to be done with the critical value method. So the p-value will not be any real use to you with the T, unless, of course, you're using technology and are willing to show your work. And not everybody is willing to do that for some unknown, perplexing reason. So if you have a TI, it does not solve all your problems. You have to do a little bit more work too. But you do get a better deal than some of the other students that didn't spend $100+ on the calculator and spent the time to learn it. But that's neither here nor there. I do not personally care, but you know who you are, whether you're a TI user or not. There really is no blend between the two. You've got to be on one side or the other. Because if you fall between the cracks, you lose lots of points on the test. So please pick a side and stay there. So most of you are on the table side of things, by the way, so that's how that goes. I don't have too much more to say. I'm still working out some details on the final coming up, but it'll definitely be heavily on Blackboard, and there will be some downloading needed, as if you want to show me a sketch or extra credit or certain other more difficult problems. But minimizing the downloading has obviously an upside to it, in that if things go haywire, which it did last time, I won't have to worry about giving you a 0 on the final. At least you'll get the bulk of the points, even if things go completely wrong. But you can help me out by trying to do it on Blackboard if possible, and not using zip files, not using Google Drive. Those are simply not acceptable. I won't have to even think about them. Those would just be zeros. So I won't even look at them. But if you've got a JPEG, if you've got a PDF, especially PDF, those are the best. So those nearly always don't have a problem. Try to submit it in some kind of order if you can. If you're not submitting very much, it isn't as important. But with a homework, if you've got 20 pages of homework that are all on different pages and you put them all out of order, I'm not going to look at it, not to the very last if I have time, because that's just a big, huge waste of time. So please help me out. I don't have much time to grade all these tests. Some of you only have 5 days to grade all this stuff, and that's a lot for 115 students who are on my roll. At least 105 who are active in this class. So that's a lot for me to do. So help me out here, and I'll try to help you out too. So that's about all there is to it. So study hard. I still have office hours, since as I speak, it's coming up on the Thursday before the finals. So I will not have office hours during finals week, because I'll be Zooming for other finals and other makeups, etc. So email, though, I can take all the way up till the time of the final and beyond. The grades are due right now on the 16th. So I will try to clean up Blackboard and give you some options here on the Blackboard here, which I'll publicize very soon. And you should be able to look at all your scores and get a pretty good idea of where your scores score is. As I've advertised before, I believe that the curve that we had in mind for the midterm should stand up for the final. Sometimes it changes by a small amount, but that should be pretty much your indicator of success. In other words, 83 on up should be an A. I don't expect that would change very much, but we'll just have to see. I'd like to give a lot of A's, frankly. I don't typically do that, but I do like to give a lot of A's whenever I can. So give me a reason to give you a good grade, and that means writing formulas down, showing steps. Some people are terrible at that. There are a lot of people who got B's that could have easily had A's if they just thought about it. And the other thing is, use the book's notation. If you're not using the book's notation, you're pretty much screaming, I'm a cheater. That's the way I have to look at it. If you pick different notation, it didn't come from our book. Where the heck did it come from? I know there may be a couple of weird exceptions out there for people who have had classes like this before, but use the book's notation and all is good as far as I'm concerned. But if you're not even trying to use the book's notation, I'm not going to really try to use all these alternate notations that, of course, WebWork has shown you. WebWork is compiled from many different people, different books, and yes, there's lots of different statistical notation out there. And if you happen to be using some illicit source, that's not good. That tells me that you're a cheater, and I don't really appreciate that because there's so many students that are not cheating. I want to give them a fair shake, and I couldn't care less about cheaters, to be honest. But that's enough of that. So please give me the book's notation, show your steps, show your work as much as you can. Whether you have to download a supplement, that would be awesome to do that as well. So anyway, try to keep that in mind. And yeah, you should only really have the book. It's going to be an open book exam, so be sure your book is all there. There's the printed notes that you found on the blue sheet in your book, and you can certainly use that. But no other source is allowed. If you happen to have some notes that you summarized yourself, that's fine. I'm not going to need to see a copy of that. I will need to see your pledge. Without it, I can't grade your paper. I'm still waiting on a couple pledges from the midterm and never got them. And I cannot grade your paper without them. That will be an F if you don't give it to me in a timely way. So please don't forget about that. But I will not need to see notes on this final. So notes will not be required, but I will need to see the pledge. So there will be a time limit, and there'll be also a downloading time limit. And if you don't stay within that time frame, either you'll get a 0 or points will heavily come off. And so stay within the time frame. Also, as of this recording, I do not plan to have backtracking. That is, backtracking will not be allowed. So you'll have one problem, you got to finish it, and you go on to problem 2, you got to finish that, and you cannot back up. There are some reasons for that. I know I would hate that as a student, but believe me, there are reasons why we do this. So you'll have to enforce the no backtracking rule. So you'll have to spend a little extra time being sure that you're good with problem number 1 before you move on to problem number 2. That's just the way it's going to have to be. I'm sorry about that. But with a curve, hopefully it'll all work out. You'll get some extra credit for that. And by now, I think you'll know that if you wouldn't even be watching this unless you were considering taking the final. But if you had decent quiz scores, well, you won't have to worry about taking the final at all. So that will affect some of you better students that already pretty much have an A clinched or whatever your chosen grade. If it looks like it's already clinched based on your quiz scores and everything else you have, that's good. You do not need to take the final. You'll either have to let me know or simply do not open the final, because once you've opened the final up, and I can tell if you have or not, then I assume you're taking the final. There is no cherry picking allowed, and I know some people might be tempted on that, but if it looks like you've opened up the final and you haven't done anything, that's a 0. Sorry. So if you're convinced you're not going to need to take the final, stay miles away from Blackboard. Do not open the final. And that way I'll know that, yes, you'd rather have the quiz scores replace your final. I don't expect a lot of you will do that. I'm guessing maybe 20% or so, maybe more. If all you want is a C and it looks like you got a C, okay. And then you could always email me and I could try to clarify things. But use the syllabus, use the percentages from the syllabus. The Blackboard may not be fixed in time for you to see all the points. But you are statistics students. We did talk about weighted averages. That shouldn't be above your head. And if it is, that kind of says that you really don't deserve to do real well in this class, in my opinion. But I guess I've been proven wrong before. But anyway, go ahead and check that out. And most of you will be taking the final, so please follow the rules. And we want to give everybody a good shake on this class. I know it's been tough, and online is never very easy. But we had a little bit of experience at the end of last quarter doing this. So anyway, we're hoping that you learn something that might be valuable in your career somewhere. It could be you're the expert in the room that is the only one that knows something about something how to save the company. And literally, I know somebody whose husband saved farmers insurance, so to speak. So things like that actually happen. And you might be in that position, and then who knows, you might have a plum job waiting for you afterwards because they're so appreciative, sending you to Switzerland, et cetera, et cetera. Well, yeah, that happened to my friend, by the way. So anyway, good luck, and email me, drop in the office hour on Thursday, the last day, and good luck on the final. Talk to you soon.